Part 3, Using Matrix Row Operations to Solve Systems of Linear Equations. Solve the system of equations using matrix row operations. We have x plus 2y equals 5 and 2x plus 2y equals 6. So the first thing I will do is write the augmented matrix. I'm using 1x plus 2y equals 5, 2x plus 2y equals 6. And I'm putting that vertical line as the equal sign. Then I need to put this in row echelon form. Anytime you're going to put a matrix in row echelon form, start with the first column. You want to do one column at a time. So the first column, I'm going to make that first row, first column a 1 if it's not already a 1. And then I'm going to use that 1 to make everything underneath of it 0. So what I mean, that first row, first column is already a 1. But I'm going to use that 1 to make the 2 that's underneath of it a 0. And to do that, I'm going to say my new row 2 is negative 2 row 1 plus row 2. So my row 1 staying the same. But my new row 2, negative 2 row 1 plus row 2. So negative 2 times 1 plus 2 is 0. Negative 2 times 2 plus 2, so that would be negative 4 plus 2 is negative 2. And then negative 2 times 5 plus 6 gives us negative 4. Once you're done with the first column, the next thing you want to do is go to the second column and make this number a leading one by multiplying that row by negative 1/2. So I'll say my new row 2 is negative 1/2 the old row 2. Remember, we can multiply any row by some non-zero constant. So my row 1 still staying the same. My row 2, I'm multiplying by negative 1/2. So 0 times negative 1/2 is still 0. Negative 2 times negative 1/2 is 1. And negative 4 times negative 1/2 is 2. Now the last thing I'm going to do is make this 2 that I'm circling here a 0, and then I'll have this in reduced row echelon form. So to make that a 0, I'm going to use the 1 that's underneath of it. So I'll say my new row 1 is negative 2 row 2 plus row 1. And that will make that one a 0. So my row 2 now is staying the same. My new row 1 is negative 2 row 2 plus row 1. So negative 2 times 0 plus 1 is still 1. Negative 2 times 1 plus 2 is 0. Negative 2 times 2 plus 5 is 1. Now if I write this as a system of equations, I have 1x equals 1 and 1y equals 2. So that is my solution, 1, 2. Now this is not always the most efficient way to solve a system of equations, but sometimes it works really well. And this, with the smaller system of equations, hopefully this helped you to see what's going on here, how we're going to use these row operations to solve a system of equations. So let's try this with a bigger system. Here we have 3 variables and 3 unknowns. So my first step will be to write this as a matrix. So my first row, 1, 1, 1, 5. Second row, 2, 3, negative 1, 2. And third row, 2, 3, negative 2, 4. Then I want the first row, first column to be a 1, which it already is. That's convenient. If not, I could divide that whole row. If it say that first row, first column was a 3, I could divide that whole row by 3, and that would work. Or multiply it by 1/3 is another way to say that. But it's already a 1, so I'm going to use that 1 to make the numbers underneath of them 0. So I'm going to use this 1 right here in the first column to make these 2 zeros. So that's the order I want to do things. Make that top left corner 1, and then make the things underneath of it 0. So my new row 2 is going to be negative 2 row 1 plus row 2, because then I'll have negative 2 plus 2, which is 0. And my new row 3 will be negative 2 row 1 plus row 3. So my row 1 staying the same. Row 2, negative 2 row 1 plus row 2. So negative 2 times 1 plus 2 is 0. Second column, negative 2 times 1 plus 3 is 1. Next column, negative 2 times 1 plus negative 1 is negative 3. And the next column, negative 2 times 5 plus 2 is negative 8. And then I'll do the same thing with row 3, negative 2 row 1 plus row 3. So negative 2 times 1 plus 2 is 0. Negative 2 times 1 plus 3 is 1. Negative 2 times 1 plus negative 2 is negative 4. And negative 2 times 5 plus 4 is negative 6. Okay, so my first column's done. The next thing I want to do is go over to the second column, and the second row, second column is what I need to be a 1. This is already a 1. Now to put it in row echelon form, I'm going to use that 1 to make everything underneath of it 0. So I'm going to say my new row 3 will be negative row 2 plus row 3. That way when I do negative 1 plus 1, I'll get a 0 in row 3 in that spot. So first two rows are staying the same. So row 3, negative row 2 plus row 3. So negative 0 plus 0 is 0. Negative 1 plus 1 is 0. Negative 3 minus 4 is negative 1. And negative 8 plus negative 6 is 2. Okay, I'm almost in row echelon form. Now I need to make this a 1. So I'm going to say my new row 3 will be negative the old row 3. So negative 1 times the old row 3. And then I have the first two rows staying the same. And that last row becomes 0, 0, 1, negative 2. Okay, so this is in row echelon form. Now I could continue and put this in reduced row echelon form, but I'm not going to right now. I'm going to do something that we call back substitution. So back substitution, and here's what I mean by that. I'm going to write this as a system of equations. So I have x plus y plus z equals 5. The middle row has 0x, 1y minus 3z equals negative 8. And the last row, 0x, 0y, and z equals negative 2. So when we're in row echelon form, we already know z. Then I'm going to go backward and substitute that z into this equation to find y. So I have y minus 3z, which is negative 2, equals negative 8. Or y plus 6 equals negative 8, subtract 6, and I get y equals negative 14. So now I know z, and I know y, and then I'm going to use both of those to substitute back into that first equation. So 1x plus 1y, so negative 14, plus 1z, which is negative 2, equals 5. So I have x minus 16 equals 5, add 16 to both sides, and I get x equals 21. So I found my x, y, z. My ordered triple for the solution, 21, negative 14, negative 2. Let's do that same one, but now we're going to put it in reduced or echelon form so you could see how we would get the same answer. So the matrix we ended up with on the previous slide, we had 1, 1, 1, 5, 0, 1, negative 3, negative 8, and 0, 0, 1, negative 2. So if I put this in reduced or echelon form, the numbers I still need to make 0 are this number in the second column, and then these two numbers in the third column. So I'll do the second column first. I need to make that circled 1 a 0, and I'm going to do that by using the 1 that's already there in that column. So my new row 1 will be negative row 2 plus row 1. So now second two rows are staying the same. So the new row 1 will be negative the old row 2 plus row 1. So negative 0 plus 1 is 1. Negative 1 plus 1 is 0. Negative 3 is 3 plus 1 is 4. And then negative 8 would be 8 plus 5 is 13. Okay, now I need to make these two numbers a 0. So I'm going to do that by saying my new row 2 will be 3 row 3 plus row 2. And my new row 1 will be negative 4 row 3 plus row 1. So I'm using this one right here to make the numbers above this one, this time 1. So this time my row 3 is staying the same, 0, 0, 1, 2. My new row 2 is 3 row 3 plus row 2. So 3 times 0 plus 0 is still 0. 3 times 0 plus 1 is 1. 3 times 1 plus negative 3 is 0. And 3 times negative 2 is negative 6, plus negative 8 is negative 14. And then I'll do row 1, negative 4 row 3 plus row 1. So negative 4 times 0 plus 1 is 1. Negative 4 times 0 plus 0 is 0. Negative 4 times 1 plus 4 is 0. And negative 4 times negative 2 is 8, plus 13 is 21. And now the solution, if we write this as a system of equations, says x equals 21, y equals negative 14, and z equals 2, which is the same solution we got before. So either method works. We could put the system in row echelon form, put the matrix in row echelon form, and do back substitution, or you can put the matrix in reduced row echelon form, and then you don't need to do any substitution. You just know that last column is your solution. Either way works. Let's try this one. Here I have x plus z equals 0, x plus y plus 2z equals 3, and y plus z equals 2. So I'll start by putting this in a matrix. The first row, 1x, 0y, 1z equals 0. Second row, 1x, 1y, 2z equals 3. And third row, 0x, 1y, 1z equals 2. Okay, so I have my augmented matrix. Now the first row, first column is already a 1, so I'm going to use that 1 to make this one 0. So my new row 2 will be negative row 1 plus row 2. So row 1 and 3 are staying the same. So my new row 2, negative row 1 plus row 2. So negative row 1, this row, plus this row. Negative 1 plus 1 is 0. Negative 0 plus 1 is 1. Negative 1 plus 2 is 1. And negative 0 plus 3 is 3. So the first column is done. Then I'm going to go to the second column. I want this number to be 1, which it already is. And I'll use that 1 to make the things underneath of it 0. So my new row 3 is going to be negative row 2 plus row 3. So row 1 and 2 are staying the same. My new row 3, negative row 2 plus row 3. So negative this row plus this row. So negative 0 plus 0 is 0. Negative 1 plus 1 is 0. Negative 1 plus 1 is 0. And negative 3 plus 2 is negative 1. Now notice that this last row says 0x plus 0y plus 0z equals negative 1, which is not true. 0 does not equal negative 1, no matter what x and y and z are. So this system has no solution. So if you get a row, when you're putting this in row echelon form, and you get a row that has all zeros except for the last number is not a 0, then you have 0 equals a non-zero number, which can't be true, then there is no solution. Now, if you get so you have a row that is all zeros, that means it's a dependent system, and you could have infinite number of solutions. But if we get a row that has everything 0 except for the number on the other side of that vertical line, if you're drawing that, then you would have no solution. So let's try this one more. Here I have x plus y plus z equals 1, negative x plus 2y plus z equals 2, and 2x minus y equals negative 1. So I'll write this as the augmented matrix first of all. And then I'm going to put this in row echelon form. So I'm going to make this one a 0. It already is. I'll use that 1 to make the things underneath of it 0. So my new row 2 will be row 1 plus row 2. That way I'll have 0 in this spot right here. My new row 3 will be negative 2 row 1 plus row 3. So my row 1 staying the same. Row 2 is going to be row 1 plus row 2. So I'm just going to add the first 2 rows. 1 plus negative 1 is 0. 1 plus 2 is 3. 1 plus 1 is 2. And 1 plus 2 is 3. Then for row 3, I'll do negative 2 row 1 plus row 3. So negative 2 times 1 plus 2 is 0. Negative 2 times 1 plus negative 1 is negative 3. Negative 2 times 1 plus 0 is negative 2. And negative 2 times 1 plus negative 1 is negative 3. Now the next thing we would need to do to put this in row echelon form would be to divide this middle row by 3, because we'd want to make this a 1. But before I do that, notice what would happen if I make my new row 3 just be row 2 plus row 3. Then I have 1, 1, 1, 1 for the first row. Second row staying the same. And if row 3, we just add the first and second row, I get 0, 0, 0, 0. So if we have a row of all zeros, that means we have a dependent system of equations. So there could be an infinite number of solutions. So that's what we have here. We have an infinitely many solutions. Now to write those solutions, I'm first going to rewrite this. So my new row 2 will be 1/3 the old row 2. So I'm just dividing that middle row by 3 or multiplying by 1/3. Okay, so now what I have, if I write this is a system of equations. The first one says x plus y plus z equals 1. The second one says y plus 2/3 z equals 1. Now I want to write everything in terms of z. So in my final answer, I'm going to have a z as the final part in my ordered triple. Y, I'm going to solve for y here by subtracting 2/3 z. And I get y equals 1 minus 2/3 z. So y, 1 minus 2/3 z. And then to find x, I'm going to substitute this in for y up here and solve for x. So I have x plus 1 minus 2/3 z plus z equals 1. And now I want to solve for x. So I'll combine like terms. I get x plus 1 plus 1/3 z equals 1. Subtract 1 and subtract 1/3 z, and I get x equals negative 1/3 z. So this is my solution to this dependent system of equations.